Hi class, it's Bill Berry back with our Java 2 video series. This week we're looking into hashing and some of the data structures that will come after we understand the basic concept, things like hash sets, hash maps. Hashing is a very interesting one because of the speed at which it can act, so it's an interesting data structure worth a little exploration. And so let's jump in and talk about it. What does hashing allow us to do? The main thing it allows us to do is search. We'll see that other things can also be very fast, but certainly searching for values that are have been entered into, that are part of the element list, right, element set, the ability to do that at near constant time, right, almost or exactly constant time. Now that's a kind of a tall order, right? Constant time means if your data set is 1,000,000 items, you're still able to add or search for something at the same speed as if you had 5. Now that's, again, very, very tall order. So let's look at some requirements if we were trying to implement this. If we were trying to brainstorm how we could implement this idea, let's talk about some ways that we might do it, and then let's talk about the way that it's typically done here, and we'll see that that's pretty straightforward. So what would we need? If we want to store integers, and it turns out really that's all we need to store, hashing only works on integers. Now you're going to say, well, but can't you do other data types? Can't you do objects? Yes, but we're going to see you're going to end up turning all of those things into an integer and then using the integer for the actual hashing. So what do we need? We need amazingly fast searching, so constant time searching. We also want add and delete to be darn close to that. We also need to store a large number of values but in a small space. So a large number of values in a large space is not the goal, because hashing means people could give you callers, right? Client code could call you and ask you to store virtually any size integer, and you need to be able to store it, but you can't have an infinite size array. So how do you do that? We also want this to scale. So as the data set gets bigger, we still want this thing to work. So how would we make this go? What are some ideas? Well, one way to do it is we might just use an unsorted array. So we could, for instance, again, we're looking for this, but we could use an unsorted array and just store values at the end. And maybe we'd say, well, when we go to delete something, we don't really delete it because we don't want to shift it. Yeah, well, we could, but notice this does not really work for us because searching would be linear. Does that make sense? So in this case, we want to make sure that we have something faster than that. So that doesn't really work for us. What else could we use? What's another approach? Well, we could use a sorted array where we put everything in a sorted list. We keep them in order, but that means we have to shift, right? Every time we go to add a value, we have to shift. That doesn't really help. And searching, even in a sorted list, the best case is going to be log base 2 of n. In a binary search in a sorted array, that's still the best that we could do, would be log base 2 of n. That's not really what we're looking for. We want something faster even than that. So doesn't really quite get it. What else could we do? So let's look at another idea here. So this starts to inch us closer to the right thinking. It's not baked, fully baked, but it gets us the right idea. What if when they gave us a value, we simply stored it at that position in the array? If they hand us, well, let's say first we got to start with an array that's marked in some way. Maybe we go through and we mark all of the items, all of the elements with a maybe negative max value or positive max value. Something that is obviously not one of the values that they could give us. Those would be the best two candidates I can think of. And then if they hand us a 37, we put the 37 at index 37. So if somebody says, hey, you got a 37, we just go to position 37, which of course is going to be constant time. And we know if it's not negative max value, if we find the 37 there, right, it's obviously not negative max value, then yes, they handed us a 37 before. So that can certainly work, but what's the problem here? To store any number that they might throw at us, we can't really do this because the array would need to be unbelievably large, and we don't really want to do that because most of the array would be empty. But can you imagine a way, can you think of a way that we could do some manipulation so that we could use the same concept but in a smaller space? Well, obviously that's where we're really going with all this, right? How do we do that? We use a hash function. And what a hash function does is it simply takes the value that is passed in, takes its absolute value because negative positions are not going to work in an array, obviously. And then notice it uses modulo math and it divides by the element, the data length. In other words, the array. This is our array. It uses the length here. So if you think about it, modulo math will always guarantee that the result of this modulo operation is going to fit into the array. Do you see why? Modulo math is a remainder, and the remainder could never be bigger than the actual size of the array. So that's the magic of what hashing does, is it uses a hash function to turn a value into an index, right? The result of this is going to be an index, and that index will always fall within the length of the array. Make sense? So let's look at some examples. Let's say we have a hash table and we have made it 7 in size just as a starting idea. What if they give us 23? Well, 23 modulo 7. 7 goes into this 3 times and 2 left over. So we take this number here, 2, that becomes the position of the array that we look at, and we store the 23 here. Make sense? If they then give us negative 581, we take the absolute value, we modulo 7, that turns out to be 0, so we store the 581 here. Again, we would want to put something in here so that we know the difference between an empty cell and a 0, right? Something that really doesn't have a value, because 0 might be a valid thing they'd hand us. And then same thing, the number can be any size you want, because modulo 7, it's always going to fit, right? And here it's a 4, and then it goes at position 4, and there you go. So a hash table is just an array that stores values that are passed in. And then to know whether we had been handed that number before, that gives us our constant time, because the number is handed to us. We again run it through the hash function. We look and see if that value is at that position, and there you go, right? Constant time. Pretty darn cool. Now, of course, this is not a flawless concept, because no matter what you do, sometimes you're going to generate the same number. That's called a collision. A collision says when you run two different numbers through the hash function, sometimes you're going to get the same position, right? You're going to get the same value out there that you're going to use for an index. For instance, we already have these numbers here from the previous slide. What if they hand us 459? Well, again, we modulo by 7. Now we get a 4 again. Well, oops, we've already got something at the fourth, at the index position 4. So, wow, what do we do about that? Well, a couple of ideas. One is, depending on the kind of numbers that you're being handed, sometimes they tend to cluster around certain areas. And if you use a prime number for the size, maybe it's going to help to kind of spread them out a little bit, maybe, depending on your numbers. Again, another is you can have larger arrays, because the larger the array, the less likely that you're going to have collisions. But no matter what you do, you are going to have collisions, right? There is no way that you can avoid it. So what are some things that we do with collisions when they inevitably pop up? One solution is called probing. And probing says, just look for another spot, right? Look for another spot and try to put it there. So a different way to do it, different ways. One is called linear probing, where you simply say, look, I'm just going to go to the next spot. If this was a collision, I'm going to go to the next neighbor and I'm going to store it there. If there's nothing here, I'll store it there. If there's nothing there, I'll move along. So you just go to the next spot. Now, as we're going to see, you're not going to let this go forever, right? Eventually this thing is going to fill up. That's a different problem. But you notice, yeah, you might have to wrap around. Yeah, you're gonna still have a devolved search if you get a lot of these things, but this is a way to do it. Sometimes rather than just looking next door, you do a quadratic probing, which says perhaps first you look 1 away, then you look 4 away, then you look 9 away, because if things are clustered, we're just going to keep looking farther and farther away from the original spot. So you can do some other interesting kind of math if you want to try to find it. Of course, all of this is going to push us from our constant time toward an n-based algorithm, right? A complexity of big O of n. But this is a start, right? This is one way to do it. Another way is you have simply a different hashing function, right? So you have double hashing. So if the first one yields a collision, we just apply some different hashing function. So all of those are potentials. They all fall under the category of probing, and that's a perfectly valid way to do this. Let's look at another way though. There's another method called separate chaining. And separate chaining says, hey, don't make the list, the array, an array of primitives. Instead, make it an array of nodes where each of those nodes have a value, like 11, but they also then have a reference. And in this case, the reference here from this node is going to point to null, right? Because there is no next value. But in this case, if you get a second one here that is a collision, you just tack it on. Either you go to the end, or at this case, just tack it on to the beginning. It doesn't really matter, right? Make it easy. So now we can search. Somebody says, do you have 11? We run it through the hash function. We come here, we go to this node, and we find it right away. If they ask us, do you have 24, we can find it right away. If they say, do you have 54, we just go down, right? Both of them made a 4 as a result of the hash function. We just linearly search until we get to null, and then we know whether it's there or not. Again, you still have this problem of pushing it toward an n-based complexity, but we're going to look at some ways to solve this. But this should look very familiar. If you're in class and you did the tree map project, the index project, you'll see that this looks a lot like our dupe and same nodes, right? These are very much like the nodes that we used in that project, almost exactly the same idea. So great. Now, what do we do to make sure that this problem doesn't get really big? Because eventually this starts really degrading our performance. So we can't let it just go forever. So what do we do? So one thing that we may want to do is create a larger array. When our array starts to get kind of full, we probably want to make a bigger one. But unlike with our array list expansion solution, we can't just copy the data over. Because notice that when the array gets bigger, the divisor gets bigger in the modulo operation, and therefore it's going to generate different results. So we can't just copy the data over, but we are going to create a larger array. What we have to do though is we make the table bigger, and then we have to run through the hash function again. You've got to go through every value that's in your old hash table, and you've got to run it through the hash function again to find its new position in the new table. Does that make sense? Think about the math. So one of the things that we often do is every time you're going to add an element to this hash table, every time you're going to hash something, you're going to first look at the load factor, and that is the ratio of the size relative to the capacity. Size being how many elements you are monitoring for them, and capacity is how big is the array. And once that starts exceeding whatever threshold that you set, in this case we believe Java uses 75. They say, hey, at 75% you're certainly going to be getting more collisions, and we want to avoid that, so it's time to rehash. So before you add, check the load factor. If it's getting too full, then rehash, which means make it bigger, rehash all the values into the new array, discard the old array. Does that make sense? So yes, that operation itself takes some time. So you want to come up with an array size that is reasonable to begin with. You don't want teeny tiny arrays that you're going to have to keep doubling or whatever you're going to do, right? You probably want to have something that starts a little bigger, gives you some room, and of course we may have constructors that let us hint at the fact that we're going to have bigger data sets to begin with. So all of these are important things in terms of understanding hashing. Now, how are we going to use these things? Well, the most important way we're going to use it is for a hash set. And a hash set is going to simply say, you give me a number and I will store unique numbers. I'll store unique values and I will let you know in constant time whether you have given me that number before or not. All right, that's the nature of a set. So we can see that pretty easily. What we're going to do is take a look at some code that uses integers first. So we'll do hash sets of integers, then we'll do hash sets using references to objects, and then we'll also talk at the very end about where can you go with this? What's the difference between a hash set and a hash map? And it turns out we have all the knowledge to understand that given everything we've studied so far. So keep watching. Next video we'll tackle a little bit of look at some code, and then we'll wrap up with one or two more videos, I believe. Thanks for watching this one though.